Good afternoon, ladies and gentlemen. We heard a lot about going to the moon and also about going to Mars, but yesterday there was some discussion, and it was also mentioned today, about going to the outer solar system. And I chose that as a subject for today because from the evolution, now we've been going to the outer solar system for 2 generations, and from the way the technique of going there has progressed, you can see the advance in technology, and it's very interesting to look at that. So actually, the interesting thing about the challenge of going to the outer solar system is not so much that it's far away. It's not really the problem. So the real problem is energy. Anything. Spaceflight is always about intelligently managing energy. So we are here inside the bottom of a fairly deep gravity well, of course not deep compared to that of the Sun or the major planets, but in order to go to Jupiter, we have to climb out of that well, first that well, and then climb away from the Sun, and then do the reverse process to go down to Jupiter. And by the way, the moon being here, that has not been mentioned earlier. People were asked what is there, in one word, the most important thing about the moon. They said oxygen is true, or the Sun is also true, but I would say just as important, location. Because we're so far outside of the gravity well, it's a very good place to go just about anywhere in the solar system. So 3 things, like in photography, 3 things are important: location, location, and location. So the way to do this, to master this energy difference, there's several ways of doing that. The first way, the old way, was to use a large rocket and to send something, brute force, directly to Jupiter. Another way is to use planetary swing-bys, propulsive maneuvers, or a combination of both, and the permutations are infinite. I go through the history now. So this is well, the example I chose here was New Horizons, but it just so much as applies to Voyager 1 and 2, Pioneer 10 and 11, or Ulysses. Though the way to get there was without anything in between. It's just a powerful launch vehicle, or a large launch vehicle and an upper stage. So no gravity assists or anything. Typically, that works only for small spacecraft because the rocket has to do so much that it can't, on top of all that, carry also a large spacecraft. And often these missions have objectives that are other than Jupiter or go beyond Jupiter. Ulysses was a solar probe, or Voyager 1 and 2, and the Pioneers went and did a grand tour of other large planets. The fastest way, it's clearly the fastest way of going there, no discussion about that. In the case of New Horizons, was just about a bit more than a year to reach Jupiter. If we rely on gravity assists, then the load of the launch vehicle is much reduced. One example is JUICE, that was launched on the 14th of April, or if we go back in time, it's Galileo or Cassini-Huygens. Cassini-Huygens went on to Saturn, of course. And the cost, of course, there's no such thing as a free lunch. And if we take the load of the launch vehicle, that means we have to do something else to get the energy into the orbit. And the way of doing that is with many gravity assist maneuvers and accepting that the transfer duration is much longer. So in the case of JUICE, it's 8 years. And now there's one thing more. If we do everything just with swing-bys, then at least one of them has to be at Venus. And that means you have a spacecraft, so engineers are met with another challenge. So you have a spacecraft that can survive the intense radiation and the cold and the dark environment near Jupiter, but at the same time it has to cope with a thermal input that's twice that at the Earth. So it's a major added challenge, and if there's a way to avoid that, it would be highly welcome. So the modern way of getting to Jupiter actually does avoid this. So this is an example here is Juno. Something had happened in between. So people had learned, the space community had learned to do planetary gravity assists, and they had become commonplace. But the one thing that was missing was large rockets that are also affordable. And the Americans have that. They have the Falcon 9. They have, they're going to have others now soon, the Vulcan series, but we don't have them yet in Europe. It's another thing we should work on, because if you don't have a rocket, you don't get to space. With a launch, with a heavy launcher, you can launch into a much higher orbit than just even higher than going out to Mars. But it's not enough yet to go to Jupiter. But you can do something in between. You can do some maneuvers here, and that boosts the orbit, and that means you come to the Earth with a much higher velocity, and you are then ejected from the swing-by with a much higher velocity. About 9 kilometers per second is what you need to reach Jupiter. And that's what Juno did. So you can see, you can see here that there's no more, you don't go down to the Venus orbit, there's no encounter of Venus. And the transfer duration here was 5 years, so it's quite a lot faster than that of JUICE. Yeah, Europa Clipper follows a similar path, but it has a different, there's a difference. They had a lucky break, and the lucky break was that they encountered Mars on the way. So you didn't need this maneuver that costs a lot of propellant. You can just do a swing-by at Mars. That will boost, that will put the orbit, the energy into the orbit. At the next, so at the first swing-by, that's enough to, you've got enough velocity to reach Jupiter. So that was really a variant with a very fortunate circumstance. So the transfer duration here is similar, 5.5 years, so similar to that of Juno. So those two technologies I just showed were similar to each other. Now the next step is one that you can use if you have a spacecraft that has large solar arrays. Because then, if the solar arrays are dimensioned to work that far out, where the power input is about 4% of what we have here, they have to be massively over-dimensioned. So that means these solar arrays will provide about 14 to 20 kilowatts at 1 AU. That's really much more than you would need to just power the spacecraft itself. So you can use this power excess for something else. For instance, you can use it for an ion propulsion system. And that will do this boost before the swing-by. So here you need 2 swing-bys because you just need more time to put in this added energy with ion propulsion. One arc is here. This is a thrust arc, this red one. And then after the swing-by, the spacecraft is in this orbit, which would then which normally with Juno would have been reached already by the launcher. There's another thrust arc here. And then the second swing-by, and then after that, the energy is sufficient to go out to Jupiter. So the advantage here is that you can actually launch with much less escape velocity than Juno or Europa Clipper. That means you can put on a larger spacecraft. And so it just means you use this excess power. You do need some ion propulsion system and xenon propellant. And, but still you can send up to 8.5 tons spacecraft with an Ariane 6.4. That's a pretty good thing, and we've been studying this now for transfers to Jupiter, to Saturn, and to the main belt, to the asteroid main belt. So the transfer duration here is slightly above 6 years, so actually there's not a big loss penalty in transfer time compared to the Juno or the Clipper way. The next step after that will be when we don't use solar arrays anymore, we use nuclear electric propulsion. Nuclear electric propulsion is impervious to the distance, so it will provide the same high power out in the vicinity of Jupiter, and it can be used to drive either a nuclear thermal or a nuclear electric propulsion system. We're going to hear more about that later. So a nuclear thermal means you have a coolant that is running over the reactor core, it gets hot and gets expelled over an engine, a rocket engine, and that provides a much higher specific impulse and therefore is much more efficient to use, and therefore you can accept higher delta Vs, and so you can very much shorten the tour out at Jupiter, may have a much more efficient mission, and also you have excess heat in order to prevent this components from cooling too much. And then nuclear electric is similar to solar electric, except that you have the benefit that the high power does not decrease as you reach high distances from the sun. So nuclear is a game changer in the outer solar system, going to the outer solar system. So you can still use low thrust propulsion out at the target, which you could not do if you had, for instance, solar electric propulsion. So it will be a completely different matter once we have those. That's the future. Thank you very much. Oops.